Yes, sir. We are able to hear you.
Okay, in the last class, we had derived the expression for f of vx, f of vy, and f of vz as the following, like this. Each one is in Gaussian. And then we wanted to find the expression for d3n xyz, and that is given in equation 5. So we'll derive, we'll see that we'll put this value into that equation. So our equation um, for d3n, which is the number of particle, a number of molecule having velocity simultaneously in the range vx and vx plus dvx, vy and vy plus dvy, and vy and vz and vz plus dvz. So simultaneously, they have the velocity component in that infinitesimal range. So that number is d3n xyz, and we found the expression to be n times f of vx, f of vy, f of vz, where f of vx, vy, vz are the individual probable velocity distribution function in x direction, in y direction, and in z direction respectively. Then we had the volume element in velocity space, like this. So we'll insert the expression for f of vx, f of vy, and f of vz into this equation. Then we'll find n times f of vx is just a Gaussian, a times. So there will be three a's coming from 3, a cube, the constant, then e power minus b. Since it's exponential, I can add all those. Vx square plus vy square plus vz square, each coming from e to the power minus b. V square is for f of vx, and similarly for f of vy and f of vz. Then the volume element dvz, and we know that vx square plus vy square plus vz square, let's add up to give you the square of the velocity, magnitude of the velocity. Let's call this equation. See, what was the last one? It was 14, so it will be 15. Now, say that this expression is given in sort of Cartesian coordinate. Okay. And as I said, that our velocity is isotropic. It doesn't have any dependence, or there is no probable, or there is no preferred direction. It's either x, y, or z. So usually, if we express the expression in terms of in like this in Cartesian coordinate or Cartesian coordinate, then it's not very interesting. Usually, the distribution is expressed in other forms, and then we go to the polar coordinate to express this expression. If we go to polar coordinate, so there is in polar spherical polar coordinate, there is a certain symmetry associated with that. Now, since it's an isotropic distribution of velocity and all, it's to preserve the symmetry of this directionality, we'll go to polar coordinate, which actually gives the which is the preferred coordinate system to express this kind of quantity when you have such symmetric. So there, where we will express the number of molecules having speed in the range, let's say, of magnitude v and v plus dv, where v is your square root of vx square, v square, and v is vz square. So we will express the above quantity in polar coordinate, where dn will be the number of molecules in that coordinate system, number of molecules having velocity or speed in the range v and v plus dv. Now, in like for position, like position coordinate, when you express your dx, dy, dz, if you go to the spherical polar coordinate, like if your x, y, z are position, dx, dy, dz from Cartesian to spherical, you write it at r square sine theta, dr, d theta, d phi, something like that. This is the volume element. Similarly, for dvx, dvy, dvz, it will be v square sine theta, dv, d theta, d phi. This is the volume element. And since the distribution is symmetric, we can integrate over the angle. Like, 1 second. Wants to join in. So in that sense, so basically we have to integrate over all the angles. So if it's like this, yeah, I'm drawing it in 2D. Let's say if this is Vx and this is Vy, then if this the velocity is r, yeah, velocity is v, not the position velocity, I'll take a different pen. Let's say this. So this dn is actually will be contained in a spherical shell of this, like this. So where the distance okay. Up to this you have v, and from here to, let's say, towards the end here, it's v plus dv in this form, and this dark area represents the number of molecules having velocity between v and v plus dv. So as I said, this is isotropic distribution, so we have to integrate over all the angle. If we do that, then our actually the volume element, so I should write it. Basically, dn represents the number of molecule within the spherical shell of radii v in between v and v plus dv. The volume of the shell of, of this cell, we have to integrate over this value. Basically, it's integration 1 over v. 1 is like sine theta dv d theta d phi. Okay. Now we have to put the limit. Like here, v goes from v to v plus dv. Theta goes from 0 to pi, that's the polar angle, and phi goes from 0 to 2 pi. So they are independent variables, so I can separate them like this: v square dv, then 0 to pi sine theta d theta, 0 to 2 pi d phi. Now these two integral represent sum of all angles, which is actually, you can carry it out, it will be 4 pi. And here it's between v plus dv and v, so it will come out as 4 pi. From here it will be as it is, v square dv. I am keeping it, I am not integrating. You can, if you integrated this in this limit, you can also get this. So this is the volume of the spherical shell. So we'll replace dvx, dvy, dvz by this. Therefore, from here we'll write it as dn in polar coordinate, and I'll take the n on the left side. Therefore, my dn, where dn is the number of molecule having velocity in the range v plus v and v plus dv. 4 pi a cube minus v square, then v square dv. That's 16. Now from the definition, this quantity should be equal to f of v dv. By definition, this is how we define f of v dv. Therefore, you can write f of v to be 4 pi a cube e to the power minus v square v square. So we found the expression for f of v, the probability distribution function or the velocity distribution function. And this function is known as Maxwell-Boltzmann distribution function. This is the velocity distribution, and this is known as the Maxwell-Boltzmann velocity distribution. Now, we have two constants, a and b. We have to find these constants. To determine the constants, we need boundary conditions, and for two constants, we need two boundary conditions. The first one being, we'll use the fact that if we integrate over all n, all dn, then we should get back n, where n is our total number of molecules. That's how we started with, right? So integral over all values of V should give me total number of molecule, which is n. So n should be dn. Dn is nothing but integral 4 pi a cube. This is n, dn. So 4 pi a cube. We have also n goes to the other side, a to the power minus b v square dv. I can take this quantity outside of the integral, 4 pi n a cube. Then I have v square, a to the power minus bv square dv. I have to evaluate this integral. To evaluate this integral, we will use some standard integral. Use some standard integral. Like integral e to the power minus beta x square x to the power n dx. This gives me something like 1 over 2 twice beta to the power n plus 1 over 2, a new function called a gamma function, capital gamma n plus 1 by 2, gamma of n plus 1 by 2. This is how the integral is defined, where gamma n is the gamma function and n is the argument. It is defined mostly like this. So gamma z, z can be a complex number. For this case, assume as real. So 0 to infinity t is a parameter, mathematical form, e to the power minus t dt in this form, or twice 0 to infinity e to the power minus t square k to the power 2z minus 1 dt. So this is how gamma function is defined. Basically, what you need to know is you have to use this integral e to the power minus beta, or some of these you can convert this integral v square e to the power minus b v square dv into one of these form, and then you use the property of the gamma function to do the integration. And then gamma n, once you find this, from gamma n you can go, you can write something like this, gamma n minus 1. This is how you can go all the way. Then gamma n minus 1 will be n minus 2 times gamma n minus 2, and finally what you will get, n minus 1 factorial. So gamma n equals to n minus 1 factorial. This one you have to use. And if we have half integral, like let's say gamma n by 2, then this becomes n minus 2 double factorial root pi 2 to the power n minus 1 by 2. I'll define the double factorial. So you may need both of these. When you have only integral, you can use the top one. If you have half integral, you can use the bottom one. And double integral is defined as n times n minus 2. You go all the way 5, 3, 1, etc. when n is odd. Similarly, n minus 2, go all the way, then you will have 6, 4, 2 when n is even, and it's 1 when n equals to minus 1 or 0. This is how it is defined. So in that case, if we determine some of these, like gamma half will be root pi. These are the frequently used gamma function which you will encounter in this course. So gamma 3 halves will be half of root pi, something like this. Gamma 5 half will be 3 4 root pi. You can get it from the top using this relationship. Okay, so far so good. Actually, we wanted to determine the constant, evaluate this integral, which I said, let's say this is equation 18, 17, 18. So using the property of gamma function from 18, we can write n on this side. I'm not doing the integral. You can do this using the above relation. 2b to the power 3 halves and then gamma 3 halves, which will be equal to 4 pi n a cube. This is pi by 3 half is root pi by 2. That is a cube. Just rearranging in left and right side, we will have, if I take it on this, n goes out. So let's try to 2 times 2, 4 beta to the power 3 halves. We have n on this side, then we have 4 pi, then again root pi, and also n. Yeah, so this is basically n goes out, 4 4 goes out, 2 pi to the power 3 halves, so beta y pi to the power 3 halves. That is a equals to b by pi. I'm taking only this root. 19. Okay, so you see that the constant a is expressed in terms of b. Like to determine two constant, we should have two conditions, but we have used only one. So from here, if we know a, then we can determine b. If we know b, we can determine a, like that. So since we have used up only one condition, so second condition we will use that we will use the expression of the root mean square velocity. From there, we will try to find the other constant, which is b. Then we can express, we can plug in the value of b, and we get the value of a from that. Because root mean square velocity is a, like if you have a distribution like this, then root mean square velocity is a good quantity to have in the expression, which you can determine very easily, and so on and so forth. So we'll take a short break here of 5 minutes. After that, we'll start. Is that okay? Okay. We'll come back at 9:35. You can refresh yourself in that time. Then we'll find B. Okay, all right. Hope you all have come back. So our plan is to express B in terms of VRMS. Now, V square RMS is defined like this. Integral V square dn over all n. So, integral V square dn is 4 pi aq. We had, what is the expression of dn? It's 4 pi aq n. The version V square, why not? 4 pi aq n V square e to the power minus bv square dv, and in the denominator 4 pi a cube n v square to the power minus bv square dv. That is, so all the constant goes away. So we have v to the power 4 at the numerator, and the denominator we have v square, and v goes from 0 to infinity. Polar coordinate, because 0 is the origin. That's why it's 0 to infinity. Otherwise, if we had x, y, z, it would have been minus infinity to plus infinity. That's what direction. Okay, on side note. So similarly, we can use the gamma function, and then the numerator 5 by b to the power 5 by 2, the gamma 5 halves, and the denominator it's 2 b to the power 3 halves, gamma 3 halves. Put all the constant, put all the value of gamma 5 over 2, gamma 3 over 2, then it will be 3 over 2b, or VRMS is V square RMS is 3 over 2b. Now we'll use another fact, is that from the is that the equipartition of energy, like VRMS, will express in terms of temperature. So from the equipartition of energy, the average kinetic energy will be 3 times half kT. Here we assume no vibration, no rotation, only translation. So total kinetic energy per molecule is 3 times half kVt, since it has 3 degrees of freedom, and 1 degrees of freedom gets half kT. Therefore, we can write kinetic energy half m Vrms square 3 by 2 kBt, or half m 3 over 2b. 3 over 2b is our v square Rms, 3 by 2 kBt. The idea is to express the microscopic quantity, which is velocity, in terms of macroscopic quantity, which is temperature. That's how we did all this going back and forth. So from here, B could be, B is m over twice cavity. this will be question number 20. So we have found A and B. So therefore, from here, you can say that A is B over pi, square root of B over pi, M over 2 pi kbt this. So we have found A and B. So the velocity distribution or the speed distribution will be, therefore, the molecular speed distribution is given by f of v. We had it in terms of the constant. Now we have the constant a cube Boltzmann constant kb to the power 3 halves, then at v square e to the power minus b v square mv square by 2 kbt. So this is the distribution which you have to remember. And this is, let's say, 22. Equation number 22. This is the full Maxwell-Boltzmann distribution. Now, how does it look like? We have expressed it in terms of like it has is a, f of v is obviously a function of velocity, but we have also temperature. So the velocity distribution function f of v depends on temperature, and velocity distribution function actually give the uh, how the velocities are distributed. And suppose you have a like we had taken a vessel where we had n molecule. Which molecule gets what? How many molecules have how much velocity? That is the distribution. This distribution represents that. So how does it look like? So first things, the molecular speed distribution, it depends on temperature. If you take the other limit, like once we want to plot it, so temperature is a parameter. Depending on temperature, the distribution will look differently. So some like if you increase temperature, as it can be seen here, if you increase temperature, then the more number of molecule we have higher speed. If we go to low temperature, then the majority of our ensemble of the number of molecules will have lower speed. So in that sense, temperature acts as a parameter in our distribution. Also, if you take this limit v tends to 0, f of v will be 0. Just take this limit. F of v in the limit v tends to 0, we have this v square term, so it will go to 0. And actually, this is a multiplication of two functions, two variables. So here, the variables are v square and e to the power minus mv square by twice kbt, and these are constant. So at the near the origin, the function looks as v square. So for small v, f of v goes as v square, because the exponential is not as fast as v square near the origin. In the other limit, v tends to infinity, f of v is also 0, because for large v, the exponential takes over, it goes as e to the power some constant v square. So as v increases, the exponential term starts dominating, and therefore the function attains, the function goes to like 0 asymptotically. So we have two behaviors. It goes to 0 at the origin, it goes to 0 at infinity, v tends to infinity. So it must pass through a maxima in between, right? It cannot be 0, 0 everywhere. And initially the distribution function is dominated by v square, so initially near the origin it goes as a parabola, then the exponential term takes over and it takes it down and makes it 0. So we are looking at something like this. If I plot it, f of v versus v, I'll explain. So y-axis, so basically what I'm plotting f of v on this axis as a function of v on this axis. So as I said, initially it is goes as like parabola, and at 0 the limit is 0, so it goes like this. Initially it's parabola, then as v increases, the exponential terms start dominating, and then it attains the maxima, and then finally you have this exponential fall. Sorry, it goes like this, attains the maxima, and then it asymptotically goes to 0. This is how the distribution looks like. And I said temperature acts as a parameter. So if I go a higher temperature, then more number of the area under the curve represents the number of molecules. So if you take a stripe here, so that many will have this much velocity, that much. If you take another stripe, so that many number of molecule will have this much velocity, and so on and so forth. If you increase the temperature, then the area under the curve will be the same. So, and more number of molecule will have higher speed. And also from the equation, you can draw it as a parameter. That is the physically you can interpret that. If you increase the temperature in the distribution, the curve becomes flat, like it goes like this, and then falls off like this. So area under both the curve is same. That because the total number of molecule is the same, so we have to keep it. Let's say this is at T2, and the black one is at T1 at temperature T1, where T1 is less than T2. Is that all right? This one. So basically, with increasing temperature, the distribution gets broader. That means the maxima occur at higher value of V. The more number of molecule are having high velocity. That's you can sort of anticipate. Now you can define another quantity, which is called the width of the distribution, or sometimes it's called the full width half maxima. So what you can do, you can take something like it's you can take full width at half maxima, half width at half maxima, whatever, and what, or sometimes they are also take at when the distribution function goes to 1 over eth value, something like that. Let's stick to full width half maxima, it's easier. So there are some convention in which it's taken. Let's say the peak is at 1, half value is here. So this is the width for the black curve, and this is the width for the red curve. Full width half maxima. I'm taking. Blue line represents full width at half maxima, or it's called at FWHM, full width at half maxima. And you find this is actually proportional to temperature. So higher temperature results in larger full width have maxima, that is broader distribution. Sometimes the way the temperatures are calculated, they calculated the distribution function. From there, they can it is related to temperature. You can if you like if you from the distribution, if you take this full width half maxima, you can calculate, then it will come at proportional to temperature. So that's the physically it means. That is why the broader distribution has larger distribution. This is the kinetic interpretation of temperature. It's not related to thermal distribution. So suppose you have a stream of molecule which is going at, all the molecule are going at 500 meters per second at the same speed. That means you have a delta function. Your width is 0. So they will speak the temperature is 0. They refer to kinetic temperature in that case. Like any molecular beam experiment or low temperature experiment, when they say that it is 0 Kelvin, no, the temperature is 0, they mean this: the distribution has a delta function. So the research in cold atoms and all, they create very low temperature. Once you look at it, it will look like red, so it will feel like it is high temperature. But since it is cut off from the surrounding and all, there is no way to define the thermodynamic temperature in that case. And when you have distribution of that such, it's always it is preferred that you will express the temperature in terms of the that is the kinetic temperature. Higher temperature results in larger width, that is broader distribution. And this is the kinetic interpretation of temperature, what we had just discussed. Okay. Any questions? Okay. So when you have this is our velocity distribution. So in here, so it gives, suppose you take a point of here, somewhere here, you take a stripe, this strip, let's say. So this is the range of velocity, and this is the f of, actually this is also number this side. If you, so this many area and f of v dv, the area under the curve represent the number of molecule having this velocity range. All right. So let's say you can define a mean or something, whatever. So let's say this is the velocity range dv, in which the number of molecule will be given by the area under the curve. Alright, so you say, okay, 300 of such molecules having velocity in the range 500 to 550 meters per second. So you have some number, and there are many molecules. So that's how they are distributed. So this many number of molecule will have this velocity, so and so forth. So how do you know that the distribution? Look, by looking at the distribution of the velocity, which one is at higher temperature and lower temperature. The broader the distribution, like the range from this side to from this side, let's this side to the other side, how big is the range? And that's to define that, to quantify that, we define something called full width hub maximum. So then you can have the range. So your velocity distribution can have, let's say, 100 to 1000 meters per second velocity, or there could be some distribution which could be between 500 to 800. So which one have the higher temperature? Which has the higher range or higher width? We don't call it range because both of them is going from 0 to infinity. What is the point of defining the range? So we define full width of maxima. And which has the larger full width of maxima, they have the higher temperature. And the consequence is that the range will be higher in that sense. So suppose you have a distribution where all the molecules are going like at exactly at, let's say, 500 meters per second at the same speed. All the molecules, you have 100 molecules, all of them are moving at the same speed. There the distribution will look like a delta function, right? And you don't have any width, and that distribution will yield a temperature which is 0, because there is no relative motion as such. So no temperature, 0 temperature. And if you have very big range or big width, that means it is at a higher temperature. So higher the range, higher the full width hub maxima, higher the temperature. Okay, then we'll stop it here.